So now we're going to start getting into the graphing applications of rational functions. But before we do that, we've got to set up a little bit of groundwork here to help us into the next video, which we'll actually get into formally graphing these. Now, um, the first thing we're going to talk about today is continuity. And based on a function, a rational function, what does that mean for the graph and what are the implications of it? So, for instance, if we have a function like this, I'm going to call this number 1, x plus 4 over x squared minus 2x minus 24, what we're concerned about with rational functions are really two things. Where are we going to have potentially a vertical asymptote, and where are we going to potentially have a hole in the graph? Those are the first two things we want to figure out. And later we're going to also add in a horizontal asymptote and some other point values we can get. But for this, the first thing I want to do is I have any rational function like that. I want to begin by factoring. So I'm going to take this x plus 4 over x squared minus 2x minus 24 and make it x plus 4 over x plus 4 times x minus 6. Now thinking back to previous videos that we've done, one of the things we want to do is find excluded values. And so one of our excluded values is at negative 4, and our other excluded value is at positive 6. Now what's happening at each of those is a completely different thing. They're undefined for different reasons. So here we have x plus 4 are going to cancel out, and the x minus 6 will not. So our function is effectively acting like 1 over x minus 6. Now, because this factor right here didn't cancel out, that means that excluded value, so x cannot equal 6, indicates infinite discontinuity. And the implications for the graph is that we are going to have a vertical asymptote, and I'm just going to abbreviate it VA, at x equals 6. So if we were to graph it, we'd see that dotted line at 6 that kind of acts as a boundary. The other excluded value at negative 4, the graph or the function canceled those out. So what we actually have here is x cannot equal negative 4 is point discontinuity, which means that there's going to be a hole at, and this is where it's different from what we did in the past, because in the past we just classified it as a point discontinuity or infinite discontinuity. But now we actually want to figure out what is the ordered pair for that hole. Well, we know the x coordinate is negative 4. If we were to take that value and plug it back into the original, we would get 0 over 0, which doesn't help us do much of anything. But we are going to plug it into the simplified reduced rational function, because that can tell us what the function wants to act like when we get to negative 4. So when I plug negative 4 into here, I'm going to end up getting negative 1 over 10. So if I were to graph this function, I would see very minutely, but it's there, that there's a hole at the point negative 4 and negative 1/10. Try another one. This one we're going to do 5 over x minus 6 squared. So here, there's really no factoring or anything to do. It's already actually been done for us. So the simplified function's all set, ready to go. Only thing I really need to look for then is my excluded value, which in this case is 6. Even though it's squared, that really doesn't make a difference for the implications we're looking at today. In the next video, when we actually start graphing it, that's going to change some things around a little bit. So our conclusion then is that there is, at x cannot equal 6, we have infinite discontinuity, which means there's a vertical asymptote at x equals 6. So that's part of our lesson here, the continuity part. Now we want to look at limits. And as a reminder, limits are intended heights of functions. So when I start plugging in values, that's actually the first thing I'm going to do is I'm going to take a number and I'm going to try and plug it in. As I look at this statement right here, the limit as x approaches 3. That says that as we're getting closer and closer to 3, what are we trying to do? So our function is x minus 3 over x squared plus 2x minus 15. So if I'm approaching a number, I'm just going to take that number and I'm going to plug it in. So check out what happens when I do that. When I plug 3 in, I'm going to get 3 minus 3 over 3 squared is 9. 2 times 3 is 6. And then minus 15. So I end up getting 0 over 0. That indicates to me that there's actually point discontinuity happening in that at that particular value. But I'm not worried about discontinuity or any of that stuff when I'm looking for limits. Limits are just intended heights of the function. So what I'm going to do is take this original function we had and I'm going to factor it. And when I factor it, the x minus 3's are going to go away. So this effectively acts like 1 over x plus 5. This is what I'm finding. The limit as x approaches 3 of 1 over x plus 5. Now I can evaluate that because that problematic area of the 0 over 0 will cancel out. And so now I can figure out what the function is going to act like. Not what it's going to be, but what it intends to act like. So when I plug in 3, I'm going to have 1 over 8 for my limit. So what happens if we take a number, and we have a limit, so x approaches 2, 7 over x minus 2. When I start plugging 2 in, this is what I'm going to get, 7 over 0. It's not factorable, and it's not 0 either. Instead, what I have to do is consider what's going on at that value. So as I get closer and closer to 2, what is the function going to approach? And so by plugging in 2 into here, I got a 0 in the denominator. Now we already know that that's undefined. We can't actually take a number and divide by 0. Remember, limits are approaching that particular value. So we never actually get to 2. We never actually get to that denominator of 0, but we get pretty darn close. So it might be 0.00000001, but it's never actually 0. So what ends up happening is we get closer and closer to 0. This number overall is going to grow and grow and grow. We're dividing by a smaller number. But something to consider is I have to consider what's happening from the left and from the right. So on a problem like this, I actually want to consider the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. And I'm going to carefully select a number to plug in. So if I'm looking at 2 from the left, I'm going to pick a number that's slightly smaller than 2, something like 1.9. And so when I plug that in, I'm going to have 7 over 1.9 minus 2, so 7 over negative 0.1. And again, what I want to do is get as close as possible to 2 as I can get, but that's going to take forever. So I could actually make this 1.99, 1.99999, and so on. Eventually what will happen is I'll take a number divided by a tiny number. It's going to give me a huge number, infinity. And so when I divide a positive divided by a negative, from the left-hand side, that's going to approach negative infinity. From the right-hand side, I'm going to approach a number that's bigger than 2, 2.1, let's say. So I'm going to take 7 over 2.1 minus 2. 7 over 0.1 gets me a huge number, infinity, but the positive value. So from the left, it's approaching negative infinity. So in other words, my graph will look something like this. I'm just going to call that 7. So it's going to approach like that, and then from the right, it's going to approach like that. What that tells me is as I approach a 7, they're not approaching the same thing, so the limit does not exist. But what if we are approaching infinity? What if infinity is the number that we want to plug in? Honestly, it depends a little bit on the degree. So as an example, we're going to find the limit as x approaches infinity of x plus 2 over x squared plus 5x minus 1. Okay, so if I go towards infinity, again, I'm plugging the biggest number that I can ever do. Is adding 2 going to really make a difference? I don't think it will, because we're going to still have a huge number. Would subtracting 1 really make a difference? Or better yet, would multiplying by 5 times infinity really change much? And the answer is it doesn't. What we're looking for when we're finding an infinite limit, and it has to do with a bunch of calculus that you guys aren't ready for yet, so we're going to skip that part. But the idea is that we're only going to look for the highest degree, and everything else goes away. So in the top or the bottom, the highest degree I see is x squared. So this, and this all go away, and I'm really trying to evaluate this. the limit as x approaches infinity of 1 over x squared. That's what the function is going to act like when I go towards infinity as an input. So if I take 1 and I divide it by infinity squared, still infinity. 1 divided by infinity would give me 0. Any number divided by infinity gives you 0. What if we had a problem where it was kind of flip-flopped? And instead of having the bigger degree in the denominator, we had it in the numerator. Our process is still the same. Since we're approaching infinity, we're only looking at the highest degree, and everything else falls by the wayside. So this really acts like 3x squared when I go towards infinity. So when I plug infinity in, if I take infinity and I square it, I get infinity. If I multiply it by 3, I still get infinity. This function will approach the biggest number ever. And then the last type is what happens when the numerator and denominator have the same degree. Something like this. So again, we're looking for the highest degree is x squared. All these others go away. This function will act like 6x squared over 2x squared when I get to infinity. So I can cancel out some things. I can cancel out my x squareds, and I can reduce my 3 or my 6 and my 2, giving me 3. So if I were to graph that function as I get further and further to infinity, the value of the function is going to achieve pretty darn close to 3. Won't actually get there, but it will approach that value.